Hi, Professor Javier. So this is the last test revision correction of the year, which was the correction for my test number 2, question 3. So mainly I had everything in the question in the initial part of it correct. The only issue that I ran into is that I didn't complete it and I had a switch and I had a sign mistake for the 740 joules that were released, and I had them positive in the test, and that was because over here, as you see, if I mark my mistake was here, I had it written as 1 over 1 minus omega rather than it being omega minus 1. So that gave me a switch of the sign. So by correcting that, you would get negative 740 joules, which supposed to have had a J there for the unit. And then I jumped on to continue out to solve the problem, and then so from the graph, from the PV graph, um, I did process 3 to 1, and delta U was 0 because we were at constant temperature, and work equals negative Q. So the way I was able to calculate work was by taking the derivative of P dV and using natural gas equation, so to use negative nRT, and that allowed me to get 552 joules of work. And since Q is equivalent to minus W, that gave us negative 552 negative joules. And the last part of the question was to find the efficiency, and then efficiency was work delivered over Q hot. So that was 1 minus QC over QH, and that gave us total inefficiency of 25.2%, which is acceptable. So my makeup problem is some of the similar problems that we have solved. So what I did is that there is a heat engine that uses the diatomic gas of 0.04 moles. With its heat capacity with constant volume is 5 over 3R. With heat capacity with constant pressure is 7 over 3R. And omega is the ratio of 7 over 5. So what the question asks you, the first is to start at point 1 with pressure of 100 kilopascal and at Vmax. The gas then goes through an adiabatic process until it reaches point 2 with pressure at 500 kilopascals and volume 500 centimeter cubed. The gas then goes to a point with constant pressure P 500 kilopascal and at Vmax. Finally, the gas returns at point 1 with pressure of 100 kilopascal and at Vmax. So we need to sketch it, we need to determine all the temperatures, we need to find every Q, U, and delta U for each of the process, and then find the thermodynamic efficiency of the cycle. So as you see here, I drew the PV diagram for it. So the first step is that I wanted to find a temperature at point 2. So I did the general ideal gas law, which is PV nRT, and then I used to solve it for T, since we had the pressure and the volume, the number of moles, and the R, which is the gas constant, and I was able to get the value of T2. To find Vmax, I used the expansion for the adiabatics, some of the equations for that for the ideal gas to find the Vmax, and I was able to find out the value to be 1,578 centimeters cubed. Then I found T1, very similar to how I found T2, and then also T3 respectively. This gave us all the values that we needed for each point: the temperature, the pressure, and the volume. So from there, I went to the processes of each one. So process 1 to 2 was adiabatic, therefore Q was 0, and then I had to solve for the work. And as you see below, using this equation here, where I did some substitutions, and I was able to determine that the work was 230 joules. Then I was able to calculate delta U for that. Then I went to process 3 to 1, which was at constant pressure. I was able to determine Q through the equation, through the number of moles, the heat capacity, and the temperature, and was able to find that Q was 1198 joules, and then I was able to find the work, which was negative 677 joules. which gave me the delta U of 521 joules. The last process was the process 3 to 1 at constant volume, giving me Q negative 2,532.63 joules, and work 0 since the volume was constant. When I calculated the efficiency, I got negative 111%. I know that's an improper value. The process was correct, is just because the values that I chose for this problem didn't work out nicely, but the idea still holds. And thank you.